Let us switch gears a little bit and talk about solubility equilibrium. So let's look at the word solubility. Solubility means how much will dissolve, how much of a solid will dissolve in a certain amount of water. So for example, this is barium sulfate. It's a solid in this drawing right here where the ions are shown, +2, -2, that's an ionic bond, that's an intramolecular force. As water goes in, it will pull the ions apart and dissolve it. Okay, so the barium +2 is dissolved because water is surrounding it. Solubility then tells you how much barium +2 and sulfate -2 is dissolved per amount of water. So the unit for solubility would be, well, if I measured this barium here and this barium and I weighed it, let's say there's 10 grams of it, and this is 1 liter of water, then you can have the solubility of 10 grams of BaSO4 for every 1 liter water. Okay. There's also something called molar solubility. Molar solubility is how many moles of that solid can dissolve in every 1 liter of water. So this is of water, this is of the solid. Mole of solid dissolved. That's called molar solubility. When you're looking at solubility, you have to also consider the equilibrium. Equilibrium means if I left the solid in the beaker for 10 years, that means that all the barium +2 and sulfate ions that's supposed to be dissolved is already dissolved. That means that as barium solid goes into aqueous, then the barium +2 aqueous goes into the solid. Those two rates are equal. That's what equilibrium means. The forward rate is equal to the reverse rate. Okay, so when a solid is at equilibrium, you can then measure how much has dissolved. And that only happens if you have some solid underneath. You must have that present for it to be at equilibrium, because some of these will go forward and some will go back. If you don't have any of the solid present, then it can't do the equilibrium. Okay, so since this is equilibrium, we're going to be studying the equilibrium constant. So as you remember before, you know that there's K equilibrium is equal to concentration of products over the concentration of reactants, right? There's also something called Kc, which is, that's pretty much the concentration. You can also do Kp, which is the pressure, products over reactants. You can also do Ka, which is the H+, A-, let's say Cl-, products over reactants, right? HCl. Well, there's also something called Ksp. S stands for solubility, which is this word solubility, product. And this number tells you how much of the solid is dissolved, or the solubility of that solid. And this is how it goes. Okay, the solubility, you know what that means, product. Let me show you why it's called solubility product. Let's consider barium sulfate as we saw here in this drawing. And as it dissolves, the solid turns into Ba+2, aqueous, and SO4 -2. So 4 -2, aqueous also. To write the equilibrium expression is just products over reactants. Okay, so let's just pretend that says equilibrium, ignore the SP for now. So it's just the same, everything that we're about to learn is the same as we've always learned before. It's just products over reactants. BaSO4. Okay. So because this is a solid, we don't write this down here because that value is not changing. The concentration of a solid is constant. Therefore, that doesn't even go there. We don't need to write it. So to find the equilibrium constant, all you have to do is take the molar solubility of that, the solubility of that, you multiply them, and you get a product. That's why it's called product. The SP stands for the equilibrium for the solubility product. Okay, well, what does this number mean? What if this number is very big? Your Ksp is huge, like 1,000,000. What does that mean to you? That means that you have a lot of these dissolving. So I'm talking like 1 times 10 to the 24. Whoa, that's a lot dissolving. What if the number is 1 times 10 to the negative 15? That means you drop BaSO4 in water and it stays together pretty much because you're going to get a little bit dissolving. Let's look at our Appendix D. In the Appendix D, you found the Ka for the acids, Kb for the bases. This is the Kb. Underneath that, you can also find the solubility product, or Ksp. Let's see how we can read this. This is barium carbonate, BaCO3. When you put that into water, how much will dissolve? Not very much, because as you can see, Ksp is times 10 to the negative 9. So BaCO3 hardly dissolves. Look at this chart and tell me which is the least soluble solid of them all. It will not dissolve in water. I'm looking at 10 to the negative 53. Wow. When you drop manganese 2 sulfide, MnS, hardly any will dissolve, as evidenced by the product of the Mn plus 2 and S minus 2 solubilities to be very, very small. Let's look at the solubility chart. Okay, it's not called molar solubility because molar solubility means the number of moles of solid over the liters of solution. Okay, so here, look at the y-axis. It is the grams. So it's not in grams, so it's not called molar solubility. It's just called solubility. It's the solute per 100 grams of water. Okay, so this should be grams. Grams of solute per 100 grams of water. Oh, right there, grams. I couldn't find that. So, and this is temperature. As temperature changes, of course, you're changing the solubility because energy could change how the water is attracted to the ions and how this is going to split apart, of course. So first, what is the solubility of NaCl at 90 degrees? To read this, you go to 90 degrees right here. You go to NaCl, which is right here. You go up. And you go over 40. So the solubility of NaCl at 90 degrees is 40 grams of NaCl for every, now you have to be careful because they're all different, of course, this is for every 100 grams of H2O. And these are the units, grams NaCl per grams of H2O. There are other possible units that they might have on the y-axis, so you just have to be careful. It could be moles of NaCl for every liters of H2O. That would be molar solubility. Okay, write the equation. Oh, I'm sorry, liters of solution, total solution. Write the equation for the dissolution of NaCl. So NaCl goes solid, becomes Na plus, aqueous, and Cl minus aqueous. Write the equilibrium expression. So the equilibrium expression will be called Ksp in this case, and it would be products over reactants. Na plus, Cl minus. What are the units for Ksp? No units. All equilibrium constants have no units. No units for this. What are the differences between molar solubility and Ksp? Okay, so molar solubility is this number right there in bracket. So whatever that number is the molar solubility of Cl minus. Whatever this number is the molar solubility of Na plus. When you multiply them together, then that's the Ksp. Okay, so let's do an example problem. Solid silver chromate is added to pure water. So silver chromate is Ag. Ag has a +1 charge always, and chromate is Craft, CrO4 -2. So silver chromate is Ag2CrO4. That solid is dissolved in water. Some of the solid remains undissolved. That's telling me that it's at equilibrium, just like the picture right here. You have to have it there for the forward and reverse reaction to occur. The mixture is stirred for several days. That means they waited a long time making sure they're at equilibrium, okay, to achieve equilibrium between the undissolved and the dissolved, okay. Analysis of the equilibrated solution, they're telling you you're at equilibrium, shows that the silver ion concentration is 1.3 E -4. So we need an equation. The equation would look like this. 2 Ag plus 1, this is aqueous, plus CrO4 -2 aqueous. Okay, so at equilibrium, the concentration of silver is 1.3 E -4 molar. Okay, so I'm going to have to erase this because this is at equilibrium. So I have to draw my icebox. Okay, so this is ICE. So analysis of the equilibrated solution shows that its silver ion concentration is this, 1.3 E -4 at equilibrium. Assuming that the Ag2CrO4 dissociated completely in water, there are no other important equilibria involving those ions. Calculate Ksp. So they gave me one number, and now they want me to get Ksp. So let me see what that even means. So Ksp, let me just write the equation first so I know what I'm looking for, equals 2 products, Ag plus 1, oh, that has to be squared because of the 2 right there, that goes there, times CrO4 -2. And of course I don't write the solid. So that's easy. I already know this number, so I'm going to plug it in, 1.3 E -4, right? And I'm going to square it. But I don't know this number. So if I don't know this number, how can I find my answer? Because they want the Ksp. So that's the problem. How do I know this number? Okay, go ahead and take a moment, pause the video, and try to figure it out yourself. Okay, so in the beginning there used to be 0 here, right? This will dissolve and go to the right. They will make 2x of this because of the 2 right here, and they will make x of this. So can you tell what x is? If you knew x, you can figure out what this is. Yeah, 2x equals this, so just cut this in half, right? 2x is equal to 1.3 E -4. Just cut it in half and you'll find x. And that is 6.5 E -5. 6.5 E -5. Because 0 plus x. So what that means is for every one of these that you dissolve, you're going to get 2 of these to 1 of these. So 2 to 1. So now that I have this number, I can just plug it into here. 6.5 E -5. And I would get Ksp then. And that is 1.1 E -12. If you look at the Ksp chart, I found silver chromate right here, Ag2CrO4, and it's 1.2 E -12. We got 1.1. Of course, the last digit is uncertain. It can change, but we're pretty close. So now you know how they got these numbers. They just took the solid, put it in some water, waited a long time, and then measured how much dissolved, and then multiplied the numbers. Okay? And that's how they got the Ksp. And Ksp stands for Solubility Product by just multiplying it. Okay? So let's do another example. In this problem, they're giving you Ksp, okay, right here, for CaF2. Assuming that CaF2 dissociates completely upon dissolving, there are no other important equilibria affecting solubility, calculate the solubility of CaF2, okay, in grams per liter. Okay, so what they want when they're asking for the solubility, they want the brackets now. Okay, so let's write an equation first. So we have CaF2 dissolving into Ca plus 2 and 2 F minuses. So what they're asking is solubility. How much of this and this? No. They're asking for how much of these will dissolve, and then we'll figure out how much this dissolves, okay? We're going to do a ratio. So just watch what we do. So we're going to do the icebox. This is solid, so we don't really put that in the equilibrium. These are aqueous, right? So we know the Ksp. We know that we have, here's the icebox. In the beginning, we have 0 of these. Okay, and then we're going to subtract here. This will form. I'm not writing any here because it's all solid. So this is x, and this is 2x. Okay, so Ksp is equal to calcium plus 2 times F minus 1 squared. Okay, don't forget that. Sometimes I forget that squared. Okay, so Ca plus 2 is an x. And then F minus is 2x. And don't forget to square the whole quantity. You're also squaring the 2. Okay, so this would be, Ksp is written here, 3.9 e negative 11. Okay, so 3.9 e negative 11 is equal to, this is going to be 4x squared times x is 4x cubed. Divide by 4 on both sides. Take the cube root. X is equal to 2.1 e negative 4. Okay, now you're wondering, what is the unit? This unit is the molarity. Molarity of what? Well, this is x. This is x, which means it's the molarity of Ca plus 2. Molarity of Ca plus 2. So what did you just find? This is called the molar solubility of Ca plus 2. Okay? What if they wanted to, because molarity is moles per liter, what if they wanted to get the molar solubility of F minus? Well, it'll be double that. So it'll be 4.2 e negative 4 is the molar solubility of F minus. Okay, so now you see the wording, molar solubility. Let's look at the question. They want the solubility of CaF2. So that's not CaF2. So what you have to do in this case, which is what everybody misses, is just do a ratio. For every 1 molar Ca plus 2, you get 1 molar CaF2. You see how I did that? So now you change the units from Ca plus 2 to CaF2, which is what they want. If they want Ca plus 2, then just leave it, but they want CaF2, so you have to do the conversion. So just for this one, it happens to be the same because it's a 1-to-1 ratio. 2.1 e negative 4 is the molar solubility of CaF2.